Hello and welcome again to another tutorial on my website projectfpga.com. In this tutorial we'll be talking about frequency dividers. So you can get the full tutorial on my website by clicking on this frequency generator or frequency dividers. So what exactly are frequency dividers? They are circuits that are used to tune frequency. You can't do without them in any FPGA design. Most of the time I didn't use them because my circuits are usually for educational purposes. If you're actually doing a real-life circuitry, it's very compulsory, because very often you will be needed to use a particular frequency to design your project, and your FPGA doesn't work at that frequency, or probably the frequency of your FPGA is quite very different from the frequency you are given. So it's very compulsory to tune that circuit. So I made this this circuit is a very short one. It helps you to tune your new circuit to the circuit of your project. So this is what the circuit looks like. It's very small, but it is a very useful circuit in any FPGA design. So you can find the code on my website. It's a very short code actually. It's very short. So this code, you'll be able to get your desired frequency from the frequency of your FPGA. So it's more like a frequency generator or divider. You call it a divider because the new frequency will always be lower than the frequency of your FPGA. Take for instance, if your FPGA works at 60 MHz, you cannot get a frequency higher. You always get something lower. So that's why it's really called a divider, a frequency divider, or a frequency generator, because it generates a new frequency. So the circuit is very small. I will explain it using Logisim. Then you would see the code, Verilog code on my website. So this is how short it looks. So I've set it properly. So this is how the circuit works. This point is where you fix how many units are you dividing the frequency with. Assuming the frequency of your FPGA is 60 MHz and you want to get a frequency of 8 MHz, that means you have to divide 16 MHz by 2. So what you should have here is the value 2. So let me show you, but it's in binary actually, so you can reset this and set this one to 1. That means you're actually dividing it by 2. So assuming your FPGA is having 21 MHz and you want to get 7 MHz from it, that means you have to divide it by 3 to get 7 out of 21. So you have to set this to 3. So this is how the divider actually works. So by how many units are you dividing, you have to set it here. Actually, you set it here in this N place. So that is where the division comes. Then you have this enable circuit. So this enable circuit is used to start the counting. So you can see here that if this enable is off, you can find out that it goes here to this particular AND gate. So, and if this AND gate is off, this multiplexer will be off. So the multiplexer will retain only what is coming into this 0 here, and whatever is coming into this 0 is what is stored in this D flip-flop. And so long as this multiplexer doesn't come on for this to change, this out counter remains fixed. I don't know if I did my best to explain it well, but if you look at the circuitry, if this enable is turned off, this D flip-flop will remain the same, because whenever this multiplexer clock comes on, the value it takes is opposite of what is inside the flip-flop. That is the negative, the opposite. So if it's 1, it takes 0. If it's 0, it takes 1. And that's how this clocks. This is what makes it to actually clock. So that is how this enable circuit starts the frequency division stuff. So the clock can be on. If your enable is not on, it's not working. Then the reset button, we all know normally what the reset button does. It resets. So we have only 2 memory here, 1 single D flip-flop and 6 flip-flops cascaded. RAM 6. I'll show you what my RAM 6 looks like. It's just a cascade of 6 flip-flops connected. It's just to store up to 6 instead of storing only 1 bit of unit. So it's able to store 6. So this is how the counting works. So that means the division the value you're dividing with won't exceed 6 bits of binary unit. That is almost like 1023 bits. 1023 in normal counting value. So once you're 10 again, this not 0 is used to turn off the counting. If this not 0 is off, okay, let me turn on the enable so you see. So the enable is on and the counter is working. But once you turn off this not 0, it takes the normal frequency of your clock. That is the frequency here. The frequency here will be going out here. This enable is used to stop it when it's off. So that's the difference between this not 0 and the enable. The two of them is used to shut down the operation, but enable halts it completely, while the not 0 is used to send the clock frequency directly out at the output. That is, looking at it, if this not 0 is on, that means it's off. That means here is on, and then the clock is also on here. So that means the clock will be going out through this OR gate and going out immediately. So that is how the not 0, the enable, the reset, and the main clock with this input, that's what they all basically do. Now the internal circuitry, how it works. So if you have your value here, whether you're dividing by 2, so what it does is to step the clock. So once the clock is turning, is actually counting here, and this RAM, what it does is a decrement per unit of whatever is going inside it. So let me explain again. So the moment you put your value here, whether it's 2 or 3 or 10, you want to divide the clock with. So, and then the first thing it does is to check if the value within the clock, within the RAM 6, I named this RAM 6. If the value within the RAM 6 is equal to 1, this multiplexer turns on and it takes in this unit here. It takes this unit here, the value here will pass into this RAM 6. And then for every clock cycle, as the clock is clocking it, you can see this subtractor here. This is a subtractor circuit. So it's constantly decrementing the value within that RAM 6, constantly decrements it. So whenever the value gets back to 1, this multiplexer comes on again. It takes back the value within this unit here. So this is what basically this RAM 6 does. It is more like a decrement counter. It decrements and counts. So it decrements for whatever value you are dividing with. If it's 10, it starts counting down from 10. So whenever it gets down to 1, it starts afresh. It takes back that value within this multiplexer and then it starts afresh. And at the point when it's taking that new value is when this particular AND gate comes on. You can see the connection between them. That is when this AND gate comes on. This is the connection there. So one wants to turn on the multiplexer and the other one goes to turn on this AND gate, and the other part of the AND gate goes with the enable. So long as your enabled AND is 1, this multiplexer here turns on. And what the multiplexer does is to switch. It's more like it's clocking. It's taking the opposite of whatever is within this single bit, the flip-flop. So what it does is, for every time it comes on, if it's 0 it takes 1, if it's 1 it takes 0, if it's 0 it takes 1, if it's 1 it takes 0. So that is how it does its own clocking. And it does its own clocking only when this is equal to 1. That is your decrement counter whenever it goes down to 1. So imagine a situation where you are. So let me explain it in details now. So if you have a 16 megahertz, so instead of counting up to 16, you are now delaying it probably by 2. You are skipping 1. So that is how the division actually happens here. So the clock will only change only when this has completely counted down. Then this will clock for 1 second. So it's not clocking now because of this not 0. Let me turn it on again so you see how it works. So you can from main side see how this and this is working. So the main clock is faster because I'm dividing by 3. So you can see here I'm dividing by 3. So it counts down, it waits. So this second one here is for the reset. You can see that it goes to the reset. So in a situation where you decide to reset the whole circuit, so the same goes for these two multiplexers. They are used to reset the two memory. So this one also is for the enable. So the enable actually turns off this multiplexer and this. So whenever the enable goes off, there is no way this one and this one will be functional. So it uses this AND gate here to turn off this one, and then uses this multiplexer here to turn off this one, and then the reset uses this multiplexer here to turn off this one, to set it to 1. That is more like turning it off, and then this multiplexer here to turn off this RAM. So that's basically how they work. But these ones are used for the counting, this one and this one here, though it's also controlled by the enable. So the frequency divider circuit is very easy. So this is where your new desired frequency comes out. You can find the code here. It's very short. It's a very short code. If you read it, you understand it better. So please, I hope there's nothing more to explain. So this OR gate here selects between two frequency. Either this one, this is the main frequency you are trying to generate, and this is the normal frequency that is coming from your, probably from your FPGA. That is when this not 0 is off. So this one goes out. But when you are doing your normal frequency generation, this one goes out there. So then I want to explain a very important part of frequency generation. This particular circuit here is a very crucial circuit in whenever you're doing any, every frequency generator circuit can look differently, but this particular circuit I highlighted is usually very compulsory. So it consists of a multiplexer that is being fed with the opposite and the normal input from a single D flip-flop. So this particular part of this security I highlighted are more like the fundamental of every frequency divider. So the multiplexer, what it does is to oscillate. So whenever it comes on, it takes, if it's 1, it takes 0. If it's 0, it takes 1. So that is how a new frequency is being generated, by oscillation. If it's 1, it takes 0. If it's 0, it takes 1. So this particular security here consisting of a multiplexer that is fed by a NOT gate and a normal input from a single D flip-flop. So it's the basic of almost every frequency generator. So whatever is powering the multiplexer determines what frequency you'll be getting. How fast the oscillation of what powers it determines what frequency is being generated. So that is it about this circuit. You can get the full code on my website, and thank you for watching. If you have any question or comment, you can leave it below. Thanks, and subscribe to my channel.